All right. Okay. Welcome back. Anyway, so today we will officially start off with the simplest. You can call it a machine learning model, or you can also. It's also been there for hundreds of years. Like it's introduced in most linear regression, in most statistical analysis, statistical classes, mathematical classes called, and it's called basically referred to as use the name linear regression. Okay, so we will introduce the background knowledge and how the field of machine learning kind of define this very traditional model using the terminology, using the basically the terms, the different styles of mathematical notation to kind of define the problem. Okay, but if you have previous course experience in statistics and statistical analysis, statistical models, you will find the very familiar content in this lecture. Okay, but I would say this is still an important lecture to go through, because we will for the first time introduce the mathematical terms and the mathematical notations and a lot of ways, a lot of terms to define problems in typical machine learning scenarios. All right, let's get started. Okay, so hopefully we can cover, the plan today is to cover the data representation and the distinguishments, the problems of unsupervised versus supervised learning problems. Okay, and I would ask also to cover the task definition and the cost function, the concept of cost function for linear regression. Okay, as for the method, two methods, we will leave them to the next week, and so there won't be new assignments released today, and the new assignments will will be online next Tuesday, after next Tuesday's lecture, and that is roughly the plan today. Alrighty. Okay. All right. I hope you still remember this plot, this figure that I put into the very first lecture. I hope I said this is a kind of a mind tool or mind map that helps you have an overall idea of typically how a machine learning model works. Okay, so we basically want to build something in the middle within the box that contains a set of parameters. Those parameters are used to describe the data that it has seen from a large collection of real data in the real world. So the typical learning machine learning model needs to take piece of data from the real world and to somehow use some mathematical transformation, use some defined logics to tune the values of the mathematical, to tune the values of the parameters. So those parameters is contains kind of the information that describes the data. So those parameters, once they are fixed through the training process, they can be used to predict new data, which is unseen from the previous training process. So this is the basic mind model for a simple machine learning model paradigm. Okay, so the first question we may have is, how do we represent the data, right? So we need features to describe them. So this is how we, the first time we introduced the features term. I think you, if you have heard of the term features before, I think it'll be easier for you to understand throughout the next steps, throughout the next examples. So let's see a simple fish classification task. Okay, the task is to, given a picture or given a real fish, you want to tell whether it is a salmon or sea bass. Okay, so it's a very easy, I won't say it's easy, but it's a simply defined classification problem. It's a binary classification problem. Okay, so if you want to learn it yourself, maybe you want to gather some bag of fish, right? And you can use a tool to measure or to observe or to touch, to smell, right? And then for every fish in the bag, you know what it is. So that's what it means to have data. Okay, those data are labeled. You are told by some experts, by fishermen, that's what each fish in that bag is. Okay, it is labeled as a salmon or sea bass. So that is the basis for learning. Okay, so we call this bag of fish your training data. All right, so given data is not enough, you need to gather structured information from the bag of, from those raw data, which are the features we will define. Okay, so say have a fish at your hand, you can use a ruler to measure it so that you got the feature called length. All right, and that one feature seemingly it seems very like simple, right, naive feature, but given that data at your hand, you can already do a lot of interesting stuff, right? Say you can plot the length, like plot the histogram. Okay, so it's basically the counts versus the counts of the particular values of length. Okay, say for example, this is what you got. We use two different colors, black or red, to differentiate the two kinds of fish. Okay, the black is for salmon, the red is for sea bass. Okay, so if we plot the histogram for the two kind of fishes, we can see a kind of a different patterns already, right? What we can claim from the plot is that, okay, maybe the majority of the sea bass cluster towards the right hand, towards the right side, because there's a red peak in there. And the majority of the salmon, on the other hand, is over the left side. So that means sea bass basically is heavier, is basically longer than the salmon. Okay, so it's already a usable model we have built. Okay, if you call it a model. Okay, so we can basically using this kind of a empirical boundary to help us decide any new examples of fish. Okay, so we can use the threshold, or you use the boundary that's length equals 11 as our basis for making predictions. Okay, so anything on the towards the left, purely based on this model, on this very simple model, we can say that as long as a fish is less than 11 inches long, inches length, as long as it's less than 11 inches long, then it's probably a salmon, right? And if it's longer than 11 lengths, then it's probably a sea bass. So of course we are making errors, right? Because this simple model doesn't even fit all the training data. Okay, we can see a lot of errors because there's also black on the right and red over on the left, right? But anyway, it's a simplistic model already learned. Okay, and we can use it to make predictions, right? So for any given fish, we just measure its length and make such a prediction. Okay? So that said, we have one feature used, which is length. Okay, so might be okay for most cases, but it doesn't. It could also necessarily. It also is not guaranteed to work for all the other ones. Okay, so a safer way is to gather more features, rather than using just one feature as length. Okay, so let's take another example. What about the lightness measured by the? Basically, you look at the pixels of a picture, okay, and you somehow measure it with some numbers. Okay, so if we look at the lightness alone, right, just like what we did for the lens, it looks prettier because there's a more significant difference between the two kind of fish, right? The majority of the sea bass still on the right, salmon on the left. We have another boundary. Okay, why not we just use the lightness equals 5.5 as our boundary to make a simple classification, okay? So for any, if we look at the second half below here, if we say if the lightness is less than 5.5, then we claim that it should be 7, otherwise it's CBES, okay? So now we have an improved model because we have two features, right? What we can do is to combine the two features. So our heuristic is having to be bimodal. So yeah, so at least from this example, I would say it supports your conclusion. Yeah, and you will see that the point of this example is that usually speaking, we need more features. So more features will be more reliable models. So if we look at these plots in the 2D space, okay, so now we need to plot two features. So now the y-axis is no longer the counts, but now we are actually splitting the two kind of fish based on the features they have. And the two fish are, each data points becomes a point in this plane, in this 2D space, okay? So different colors indicate the species. And we kind of have a pretty good model now. And the model can be indicated by the line that separates all the examples here. And this line is something we can call decision boundary, okay? Because it separates the two kind of targets, species, right? And the feature we use is now a vector, okay? It's a 1D vector that has two elements. First lightness, second length. It's not a single feature. It's no longer a single feature, okay? Yeah, it's a good question. How do we decide precisely where decision boundary should be? That is what most of the machine learning models is trying to do. So it's trying to use some criteria, for example, to minimize the error rates, to maximize the correctly predict examples, or to maximize the distance between the boundary and the nearby data points. Those are all different strategies, and we will see. We will gradually lay out a map towards that goal to trying to find a decision boundary between examples. Alrighty, okay. So we're happy now because it's a pretty good model. And if you look at one example data in it, we'll see that, okay, this fish, it has a lightness equals 2.1, length equals 16.5. And those are typical examples of Seaman and the CBES, okay? But still, we need to be careful, right? Because some features may not be good. We're lucky and we pick the length and the lightness and it works pretty well. But how about let's use the number of eyes? Well, apparently it doesn't tell anything because the two fish, these two species, they all have two eyes, right? How about weight? Okay, weight may be a useful feature if we use it alone, but it is not sure that if we'll add anything, because we already have lengths, and the lengths, I think they are strongly correlated with the weights. The longer fish tend to have larger weight. So it is not sure. It is not clear whether adding weight as a feature, as another feature, will add more performance to the model. And color, yeah, color may be a different feature, but it is also somehow maybe related to the lightness. Yeah, smell. Smell could be because it's a different totally new modality. So if we can somehow quantify smell, then I'm pretty sure it can add more information. Okay, so anyway, the point is that the features need to be carefully chosen, carefully selected, okay? And those, the features we talked about so far need to be manually collected, okay? Those are more of a traditional type of feature that in the early stage, machine learning models in the early stage rely on. Okay. All right. Now let's look at a different issue. All right. So different machine learning models may draw boundaries differently, because previously we using lightness and lightness and length as two features. We can draw a straight line as a boundary. Okay. But of course we can draw a more much fancier boundaries rather than a straight line. Okay. Say, for example, these are the two simple examples. The first on the left is a boundary as a straight line along the y-axis, right? Anything that is on the left, anything on the right are clearly distinguished. And the second example is a linear line, right? But with some angle, with some slope, okay? And the third type of decision boundary is kind of more interesting, right? Because it's a curve, right? It's a smoother curve that try to fit the data more so that it makes less error prediction. It makes less mistakes, and this curve is towards the C base because it tries to encompass. It tries to include as many C base as possible, but without taking too much black dots into the realm of the C base. Okay, so let's look at another extreme examples, which is a much more sophisticated boundary. Okay, so this fourth type of decision boundary is kind of worrying, but if we look at the outcome first, right? If we look at the outcome, it may be maybe it can outperform the decision boundary on the above, or it also can maybe better than the boundary on the left, because you see the black dots here, it is correctly classified as salmon, right? And the red ones here is also classified as sea bass because according to this boundary, it's making predictions. So compared to something that directly splits these two areas, it can have better performance in terms of how many correct examples they are predicting. But we need to think about whether this is the best model, right? So the problem of this type of model is that it is not friendly to new data. It doesn't generalize well, right? Because, for example, if I have a new sea bass coming in at this point, right? I draw a new red dot here. According to this very sophisticated model, these new dots falls to the left of the boundary. So this model will claim that these dots should be salmon, right? But apparently it looks like more closer to the center of sea bass. Yeah. I see someone raise hand. You can actually directly unmute and speak if you have questions. Okay. Yeah, so if we use the term in machine learning, then we can call this as an overfitting. Yeah. So overfitting means that we are fitting the data too much. We're trying too hard to draw a sophisticated decision boundary so that less error is made. But with the cost, with the price that we didn't generalize the patterns. We didn't gain general knowledge, general information about the classification problem. Okay? We're just memorizing the data. Okay, that is not an ideal machine learning are expected to behavior. Okay, so we will talk more about this problem of overfitting in the future. And today, now let's just go to the next slide. All right. All right, so it's a little bit recap here. We use an example of fish classifier to lay out the technique or lay out some concepts that we will keep using in this class, which is to find the features out of data and try to represent each data point with a feature vector. Okay, so in the next few slides, we will cover more examples of this paradigm. Okay, so this 6-step procedure using this feature classification example is something that we're gonna actually find in a lot of machine learning scenario, applied machine learning scenarios. Okay. All right. So now let's look at this paradigm. If given the training data, the first step is to extract features in the form of a vector of measurements, like including, for example, weight, length, color, right? And the labels is something we want to predict. And in this case, it's salmon and sea bass, right? And after the model is trained in the given, in the testing stage, we're usually given a bunch of testing examples. And the model will be applied to those testing models by we will compute the feature vector for each test example and then combine and then apply the models upon the test examples. All right, and the job is to predict the label Y. And this is also known as a paradigm for supervised learning. But we will find another example for unsupervised learning later after a few slides. Okay, no more cases for flower classification. It's more or less typical, more or less the similar example, but with more with more labels, with more target variables to predict, including the 3 types of flowers, right? And also more features used compared to our salmon versus sea bass example. So this sepal length, petal length, petal width, sepal width. This is a famous example for data science classes produced by UCI's machine learning class, okay? And in this case, the vector is 4, like we have those lengths, those measures included in one row, right? So that's one example. Another example is for autistic spectrum disorder detection data sets, okay? And in this example, the feature vector is much longer. So we're looking at this data from purely technical perspective. The features, the target is binary, is to predict whether a person is positive or negative with has positive versus negative diagnosis of this disease. Okay, and the feature vector is 21. Right? If you look at the features, those are very heterogeneous features. Okay, we may have binary features, we may have integers, strings, booleans, integer numbers, strings, right? Okay. Third case is digital recognition. Okay, so this one is in terms of from the perspective of feature representations, the data are quite different from the previous ones because those data are no records data. The data to be trained on and to be recognized are pixel data. Okay, so if we want to define the features, we need to view the data in a different way. Okay, so we'll see that in future examples, in future assignments that we have similar tasks that try to recognize the pictures of sign languages, which are pictures of the hands. So we basically need to convert a picture of pixels into a long feature vector. Yeah. What do we have to make edge detection or most important vectors? So edge detection is a term in computer vision, and nowadays the state-of-the-art image recognition or object detection models don't explicitly use the low-level features such as edges, but these edge detection steps are automatically included into the large convolutional neural networks. So we will introduce that parts to compare to when we introduce the deep neural networks. We would have some slides covering that points. So how the low-level features are automatically aggregated into high-level features. So in practice, the edge detection is not manually set for modern computer vision tasks. Okay, insurance company example also uses a bunch of long feature sets like numbers, binaries, strings, okay? And in the ripeness of fruit detection, we also have feature vectors like size, weights. Yeah, these are just examples to show how data representation are practiced in real-world machine learning applications. All right, so lastly, it comes to the part for the supervised versus unsupervised learning paradigms. So we're gonna spend one slide on this, actually 1 or 2 slides. So supervised machine learning is to create the map between feature and labels, okay? So we want to learn what kind of features leads to what kind of labels. And the test samples used in this case only has features, okay? And the task is to predict the label from the features, okay? While on the other hand, the unsupervised learning, the training data includes only features and they are not labeled, okay? And the task becomes a different task, which is to discover the patterns in data, right? For example, to cluster data into groups or to reduce the dimensionalities, okay? So these are very different two types of machine learning problems, but I think it's also easy to distinguish them, okay? So in the next slide, we'll have feature. We would have, these 3, actually we just, primary focus is on the first 2 types, supervised. Oops. Supervised learning. If you look at the training data, if you think of the orange and blue rectangles as matrices, as data, okay? If you look at one row of it, it's just one instance or one example, okay? And the training data for supervised learning, they have features and the one column of labels. But for training data, it usually looks like there's only features, okay? There's no actual labels. And in the case where we have part of the data labeled while the other of the part unlabeled, then it's a kind of semi-supervised learning problem in which we can use a bunch of techniques to infer those unlabeled data using the existing information, right? So this is some technique that people are enthusiastic about years ago. Okay, I think there's still research going on about this in this field. All right. Okay, there's one more visualization for the supervised classification versus unsupervised. Okay, so using the flower example, iris flower example, if we have labels available, then we can differentiate different colors, differentiate the 3 types of flowers with colors. So with them plotted in this 2D dimension, we can easily check the differences between all these kinds of, between these 3 types of flowers. But if we don't have the labeled information, then it will be like this. So there won't be color information in there. And all we can tell is that, okay, there may be a cluster here, there may be a cluster here, but we can no longer split among these clusters, okay? So this example is also to show how the 2 paradigms differ among using the data, visualize the data as an example. All right. Anyway, that's a little recap for what we have covered about the types of machine learning problems. And I think we are pretty much prepared to look at the linear regression problems now, okay, with the knowledge for data representation, for data preparation steps are pretty much covered here. All right. So let's look at the task. How do we define the so-called machine learning problem? Okay. The linear regression problem. All right. So think about the task of predicting the housing price. So the price is the label, okay? Is a label we want to predict. And we usually use the letter Y to indicate the label, to denote the label. And the price, this label is a continuous number. It is a real number or float number that has continuous range. That is not a binary, or it is not a categorical, okay? So that's why we call it a regression problem, okay? And it belongs to the field, it belongs to the realm of supervised learning, because we will have existing data that has labels to train a model, okay? So think about features, right? If we want to predict the price of a house, there are a bunch of features we can use. The most important features like size and number of bedrooms, school districts, which is the area, right? And in which year it is built, right? And a bunch of other features we can include, right? So let's start with one feature. If it's a regression with one single feature, what would it be like? Okay, so let's look at if we take the size as the one feature to predict the price, and the price is in $1,000, and the size is in square feet. Say we have collected a bunch of data, all right, from the markets, and we can plot the data by price versus size on these charts. Okay, so that's what we've got here. Okay, and if we list all the training data into our into a table view, it will be like this. Okay, so the features is something we use X to denote. It actually corresponds to this size, and the label Y1, Y2, Y3, they actually correspond to the price. Okay. And then also there's some details here. The superscript I here, okay? If we put I within the superscripts and within the brackets, within the round brackets, it indicates that this is our I's data instance or data example, okay? And the future on, let me, all right, and in the next slide, we're gonna look at the way that we, the notation that we use for the parameters, okay? So it's a linear model, linear regression model. So we would use a linear combination to make the prediction. And by linear combination, I mean, we use the parameter theta1 times the feature, theta1 times X, to make our prediction. Okay, so this is a very straightforward model. All right. If we look at going back to the mind model for all machine learning models, it is somewhere the features is like this. We would have theta0 and theta1, okay? And these are the only parameters that we will use for fitting the linear regression model. And we can see additional theta0, right? Because in the previous stage, in the previous slide, we only have theta1 times X. But now why do we have a theta0? So this is called an intercept parameter, right? Because using these intercepts, we're able to, we're holding the assumption that when the size is so the slope, so the curve will not go through the 0 points. Okay, so all you can think of theta 0 as some base price for predicting house prices. Okay, so with the goal in our mind to predict the house, we can build a linear model that looks this way. Okay, if we use f of theta to describe the linear model, okay, and the input is x, then the mathematical equation is theta 0 plus theta 1 times x. Okay, and that's pretty much it. That's the model we define. Okay, so given this simple model, we're able to train a model. Okay, this is how we define the model, and then we're gonna train all the thetas in this model. Okay, and the theta 0 is the intercept, theta 1 is the slope, right? And given a model that's already trained, yeah, y is the label and x is the feature. That's correct. Okay, so assume that we have already trained theta 0 and theta 1, then we will be able to make predictions in quite an easy style. Like we can simply use this parameter directly, like theta 0 equals 50 and the theta 1 equals 300. So the price for a house of 895 square feet is simply to plug in the result of plugging all these numbers into the equation and get the results. Okay, so that's the layouts of how the models look like. Okay? And if we look closer at the meanings of the parameters, we will find that they also carry significant statistical meanings. Like if the theta 1 is 0, right? If theta 1 is 0, which is unlikely to happen, but it doesn't, it means that the house price will not change no matter how your inputs, no matter how the size of your house changes, right? Then if the theta 1 equals 0, it means that it will go through the 0 points. So if we have a house of 0 square feet in the house, the price will be 0. So which is also makes sense, but usually when we fit a linear model, we don't leave the intercept to be 0. Okay, and we can have somewhere in between. We can have a different theta 1 and different theta 0. And if you compare the larger theta 1, which is 0.177, with the smaller theta 1 here, 0.11, you can see that the slopes are different. So for the blue curve will grow stronger and grows faster, and the blue one grows slower, which means the price relates to the size with different strengths of correlation. Okay, so those are the meanings of the thetas. All right.
I got a question.
Yes.
How come we're showing different lines? Isn't there like a best fit linear regression?
Which slide are you referring to? This slide?
This line, this one right here. Like you have 3 different lines. It's like I understand. Like I don't know. I just thought like in stats, like there's like a best fit linear regression.
Yeah. This is not the best fit yet because we haven't plotted the data points yet. So on the next slide, I'm going to show how do we find the best fit to the data points.
Professor,
Yes.
I have a question.
Yeah.
To find the value of theta 0 and theta 1, I think we only the 2 records would be enough, as there are only 2 variables. For example, I mean, if you have 2 instances, we can find the value of theta 0 and theta 1.
Yeah.
And now the third instance won't be lying on this function, might be. So how to keep on accurating the line, the actual values of theta 0 and theta 1, when two instances can give us a good value, then third will disturb it, fourth will again disturb it. I mean, it's kind of, we need to come up with some kind of a formula where we keep on refining our theta 0 and theta 1.
That's correct. So the simplest case is that you have 2 points, and in 2 points you can just write you can just draw a line that goes through all the 2 points. But with more than 2 points, like 3 points, they are not necessarily lying on the same line. So you need to specify some rules to draw the lines that satisfy those rules. And by those rules, I mean, we want the line to be a good description of all the data points, right? We want the line to be as close to those data points as possible. We don't want to randomly draw a line that didn't tell anything about the pattern in the data, right? So that is exactly what we're gonna do in the next slide.
Okay.
Yeah.
Thank you.
So how do we find the best theta and theta 0 and theta 1? That is the question that we need to keep in our mind. Okay, we may have different options. Like we can just randomly draw a red line like this, but that is totally irresponsible because we can tell that from our eye that it is not reflecting the trend of the data points, right? I see Robin's question that for each new data point, we adapt the new thetas. So it kind of describes the training process, and we will see how those thetas are gradually obtained during the training stage. Okay. All right. So this red line is not good, right? Because it's not kind of describing the trend of the black dots, because the black dots should grow slower. And also this yellow curve, the trend seems more correct, but the intercept is not correct. It's too far below, right? It's not at the correct level of the house prices. So among all these 3 curves, I would say the blue one seems a better option, seems a better fit, or correspond to a better theta 0 and theta 1. Okay, because it's close to the actual data and it's kind of describing the trending of the data points. All right. So our question is that how do we find those theta 0 and theta 1 so that the model is close to y, is close to the price for all the training data points. Okay. For all the training data points in our training sets. Okay, so these I's include all the data examples. Okay, right, now this is what we're gonna solve by defining close first, right? We need to quantify our standard of being close. Okay, so now let's invent some new notations here. We give y a hat, and this is called y hat. And y hat is our predictive value given the theta 0, theta 1, and the inputs xi. Okay, so xi is among the training data sets. Okay, and this is how our actual data looks like. Okay, so for example, we have theta 0 and theta 1 that draws such a line. And we can also plot all of the existing training data points onto the same plane, onto the same 2D space, right? We have x1, x2, y3, x3, x4, and so on, right? And we can also plot the predicted points. Okay, so what is the predicted points? The predicted points has the same x coordinates, right, with the real data, but the y coordinate is y hats instead of actual y's. Okay, so this y hat is the predicted value given an x, right? It's all the predicted points falls onto the model's line. Okay, that's how the model is defined, right? So these y hats are on the line. Okay, and remember, we want the line to be as close to the actual data points as possible. So now we will use these y hats to define the closeness or to define the distance. Okay, we will use the distance between these y hats with the actual y's to define the close. Okay, and our objective is to minimize those distances. Okay, so this is out of intuition, right? If the distance are too far, then the model deviate too much from the actual data. So that is not something we want. So intuitively, we want the model to be, we want the line to be as close to the actual data as possible. Okay, that is, we want the y hats to be as close to the y as possible. Okay, so given this goal in our mind, we can define our learning objective, okay, which is to minimize the difference between the predicted value y hats and the ground truth y. Okay, so we call yi the ground truth because they are in the training data, they never change. We think of them as truth. Okay, so we can use this form, this summation of squares. Okay, the first square is the distance, is the difference between y1 and y hat 1. Okay, we compute the difference and compute the square of it and sum up with y2 minus y2 hats, sum and the square, and so on. So this is how we get all the information here, or get all the distances here. And we sum up all the distances and we try to minimize this formula. Okay, so this defines as a cost function, okay, which is a measure of how correct the model is in the task of mapping x to y. Okay, we can use this sum of squares to define our cost function, which is the mean square error. Okay, this cost function j of theta 0 and theta 1 is defined, use this sum of squares divided by 2 of m, and m is the number of instances. Okay, so it's basically the mean of the sum of squares, and in short we call it mean square errors, MSE. Okay, and the y hat here, notice that the y hat here is derived from the linear model. Okay, the linear model is a function of it's a function based on theta. Okay, so it's basically theta 0 plus theta 1 times xi. Yeah, if you supply xi as the input. Okay, and yeah, we've defined the mean square error as our cost function. Okay, so here we need to notice that the cost function j is a function of theta 0 and theta 1. Okay, and to us, theta 0 and theta 1 are unknown. It is something we want to find, right? And the data xi and yi, they are actually known to us because we collected the training data. Okay, so given the mean, given all the data, we want to find the thetas, the theta 0 and theta 1 that minimize the mean square error for us, and that is our learning objective. Okay, so we still have some time. So far, anybody have any questions to the contents so far?
What is the M again?
So M is the number of data examples. So this summation ranges from 1 to m. So that means we collect all the, we add up all the data examples. And in this case, the m is actually 5 because we have 5 data points. Okay.
Professor, and do we also need to know why this is 1 divided by 2m and why not m only?
Yeah, we will. I think that will be easier to understand in the next lecture. When we take the derivatives of the cost function, these two will eliminate with some constant here. So that makes the thing more beautiful. Yeah.
Okay.
Yeah. Yeah, I see the same question in the chat. So the theta 0.
Can you remind me what the definition of the task definition is?
Yeah, so the task is to find a model that find a model that predicts the price. Predict the price using the size as input. Okay, and we are building a linear model, and the linear model is basically a linear line that can be described by theta 0 and theta 1. And theta 1 is the slope, and theta 0 is the intercept. Okay, so it's two numbers. So these two numbers define a model, and we want to find the best model because we want to predict the price as accurate as possible. So what is a best model? So the model that we think is best is the one that is the closest to the existing data points. Okay, so that's basically the task here.
Thank you. Yeah.
Yeah. Yeah, it's also called least mean square error maybe in statistical books. So the theta 0 and 1 are what the computer gives us after running through the feature x and y. Yes, exactly. So the theta 0 and theta 1 will be returned by the training stage. So after training the model, will be given the theta 0 and theta 1, which are the model's parameters, which is our information about the housing price markets. Yeah. Okay, so no more questions so far. Okay, so good. It's quicker than I thought. Then we can proceed on to the next slide. Okay. Let's cover a little bit about the methods of solving the learning objective. Like based on the learning objective to minimize the mean square error, how do we solve the problem to obtain the theta 0 and theta 1? Okay, so now we need to do a little bit math. How do we solve the minimization problem? Right, we want to minimize the cost function. Okay, the cost function is defined by this form, right? It's a quadratic term. So, and as I write on the previous slides, this is our model. So this f of theta of xi actually is this one, right? It's theta 0 plus theta 1 times xi, okay? So if you write it, expand it into this form, and also expand this quadratic term, it'll be something like this within this very long equation, okay? So you can try it on your paper, but if we observe these two terms, we can already see that the first half here, it's about theta 0. And the part on the right, let me use a different color. The part on the right, it's about theta 1, and also let me use a different color. There's some theta 0 and theta 1 term here. Okay, so keep in mind that the theta 0 and theta 1 are the unknown variables we want to solve. Okay, and the xi and y's, they are knowns, they are data, they are constants. Okay, all right. So we can simplify the term like this, because it's basically a quadratic function, right? It's a quadratic function in the form of a times theta 0 squared plus b times theta 0 plus c times theta 1 squared plus d times theta 1 plus e times theta 0 times theta 1 plus some constant d. Okay, we can write it as such a simplified form. So it's in nature a quadratic function. Okay, And also we know that the A's and C's, they are greater than 0. Okay, A's and C's, the quadratic terms coefficient are greater than 0. So it's a good news for us, right? We basically know the shapes of the function. Okay, so the quality, the property of a quadratic function is that we can find the minimal points of it. Okay, if we look at a one-dimensional, a one-variable quadratic function in this general form, a times x squared plus b times x plus c. If we draw it on the plane, it should be like this, right? If we draw a quadratic function like this, and we can always find a minimal value whenever its derivatives equal 0. Okay, that's where it is. Okay, so in this point, the quadratic function has a minimal value, and we can find these points by taking the derivatives of the function, right, with respect to our unknown variable, which is x here, and let the derivative to be 0. By solving this equation, we can have that x equals minus b divided by 2a, right? And that is where x is. That is where x is. And within these points, x equal this value, we will have the minimal value for the quadratic function. Okay, and we'll take the same method because the cost function is also a quadratic function, and the quadratic terms coefficients are greater than 0. That means it's safe to take such a derivative method. Okay, and our unknown variables are theta 0 and theta 1. It will reach the minimum value when the derivatives of the cost function with respect to theta 0 and theta 1 both equal 0. Okay, that is our information we have. Okay, so another piece of technique we will need to use is that the theta 1 can be treated as a constant when we are computing the derivatives with respect to theta 0, and vice versa. So when we take the derivatives with respect to theta 1, the theta 0 is also a constant. Okay, so let's quickly do that. J of theta 0 and theta 1 looks like this, right? It's 1 over n times a summation of bunch of squares. Okay, now if you take a derivative with respect to theta 0, then the two, we are following the rules of taking derivatives, right? We take the 2 out, right? And eliminate it with the 2 in the denominator here. And also within the term here, because it's theta 0, we are focusing on here. Only in the theta 0 is the variable. So we will need to take the coefficient -1 out, right? To take it out here. And this is the derivative of j with respect to theta 0. And we want it to be 0. Okay, because at 0 point, we will have a minimal value for the j. And we'll do the same thing for theta 1. If we take the derivative with respect to theta 1, right, we will have basically the same thing here, but with additional coefficient xi, because inside the square, inside the brackets is theta 1 times xi, right? And xi is treated as constant. So this constant will taken out, okay? And it's also we want it to reach 0, okay? So now we have equations to solve, right? And those equations are not those hardest to be solved, okay? If we write it, if we split the terms and write it again, we will find that it's basically can be simplified to these two equations. Okay, the negative of y bar, and this y bar means the mean values of y, plus theta 0. Yes.
So on the second bullet point, you pulled out a negative. How come you didn't put inside the parentheses positive?
You mean I didn't put the positive inside?
Yeah, because you took out the negative, right?
Yes, I take out the negative. That's correct.
So then shouldn't the inside be positive? Like that should be plus for theta 0 and then plus theta 1.
Oh, so you mean this one should be positive, right? The negative times negative.
Yeah.
Yeah, that is positive here.
Right, but he's confused in the same way that I am. That like, why didn't the negative flip? Like, why is the second row the negative was fine? That you're like, what makes it different? Like, why did the negative need to switch from the first row to the second row, but then the inside also didn't change of the term? Is that where you were getting at, Isaiah?
Yeah.
You mean from the first row to the second row?
No, the row above that. So yeah,
like this?
there was no negative in that first row. It was just 1/2m. But
Yeah.
then in the next row, the negative came out of the equation, but nothing else flipped, which confused us.
Yeah, the negative is taken out because the coefficient before theta 0 is -1. We're treating theta 0 as a variable. It's the chain rule. It's a chain rule of taking the derivatives. Let me see if I can explain this here. So if we think of, let me first clear all the output here. Let's refer to this whole thing within the brackets as something like A. Okay. So we want to take the derivative of J with respect to theta 0. So it should be take the derivative of this sigma A square with respect to theta 0. Okay, so it should be 1/m times the sigma of, take the derivative of A with respect to theta 0. Okay, so now we just need to focus on these terms. Okay, so A is yi minus theta 0 minus theta 1 times x I. If we take it with respect to theta 0, it will give us -1 because the -1 is here from the coefficient here. If we take the derivative with theta 1, it will give us the -xi.
Professor,
Yes.
just a correction. The first line should be A/m at the top here, right hand side. Right hand side, it should be A divided by m. No, I mean next one, next statement. Here, yeah.
A divided by n.
No, here m. You wrote 1 divided by m. It should be A divided by m. Because derivative of A square is 2A, and then derivative of.
I can actually allow for drawing, if you can correct me, allow for enable annotation for others. Yeah.
Can I?
Yeah.
I was just saying after this No, I cannot draw it.
You cannot?
No. I was just saying this, when you wrote it down 1 upon m,
Mhm.
it should be a upon m. Because the derivative of a square is 2a multiplied derivative a.
Mhm.
That's what I'm saying. I'm not sure how to draw it here.
There's an annotate button.
Yeah, I can see it now. Here it is. I was saying after this here,
Mhm.
it should be 2a and then derivative of a by theta.
Theta 0, yeah.
Yeah, and this 2m is there, still there, 1 upon 2m. So 2 get cancelled, it becomes a by m. Over here, it should be a upon m. So this is a. That's something. This should be a. That's the reason we have a over here. This is a only. This part.
No, no. We shouldn't keep a there.
We should keep a there, right?
We shouldn't.
No, a is here also. This part is a only. When
No,
you use this.
if we apply the chain rule like this,
You do the math later.
yeah, I think the math is important. But anyway, we have time because I was planning. This one was planned for next week's content, but we can start earlier here. So applying the chain rule is like the derivative with respect to theta 0 is something decomposed into two parts times big theta 0. Yeah. If I can clear my drawing. So the A is here, J. Finally, we want to J with respect to theta, and it can be decomposed into J of the derivative with respect to A times the derivative of A with respect to theta.
Is this the type of material that we're going to need to know for tests and assignments, or is this just more so to help our understanding? Because I have not done calculus since high school.
Yeah, so these are the bases for understanding the so-called derivative methods or gradients descent methods that we're gonna talk about in the near future. It is definitely helpful to have a brief review of the chain rule of calculus. So it's basically, I think the previous points that we've been discussing is that if we treat this one as A as complete, then these will give us 1 over m sigma A, right? The A will not come out. And this one on the right will give us, depends on theta 0 or theta 1. If it's theta 0, then it is -1. Right.
Yes, Professor. I was talking about this A only, which you wrote now over here. This one, this A I was talking about that time. This A divided by M. So maybe it's a different style of doing calculus, but I was also doing the chain rule and saying this A should be there, which I thought was missing. But I got your point.
Yeah, A should sigmas within the sigma, but not outside the sigma, right?
Yes, yes. True.
Yeah.
Yeah.
Yeah. So similar calculation for the second equation can be done, which is to compute the derivatives with respect to θ1, which will give you the equations finally like this. Okay, and the x bars and the y bars, they are actually the mean values of your data. Okay, that means they can easily be obtained. Okay, so I will finish this slide, and it means we can solve these equations, and the solutions are directly given by these normal equation solutions, which means we can solve the θ0 using the mean values of y minus θ1 times y hat times y bar, and the θ1 is a more complex form, but this is known as the covariance between y and the x, which is also computable, calculatable. Okay, so given θ0, yeah, we will definitely reveal this in the next class. So θ0 and θ1 are wanted; they are the returned model parameters. So these will be directly obtained from the data, okay, which is good news for us. That said, given a bunch of data, we're able to compute θ0 and θ1 that fit the data, okay? And we will see the difficulty of these normal equation solutions, because when data are big, this method is really not that fast to compute.
Professor, just a quick question over here.
Yes.
The θ1 is dependent upon yi, instant of y and instance of x. So every instance will give us a different value for θ1?
No.
Oh, it's a summation. It will be like all together. Okay.
Yeah, it's a summation. Yeah.
Okay.
Each data set will give us a fixed θ1.
Okay. Thank you.
Yeah. All right. So given θ1 and θ0, we can do our predictions, and we are basically done with training our first machine learning model. If we call a linear regression model also a machine learning model, okay? But similar, basically everything here is on paper, and we don't describe how we do it computationally. How do we implement it in with Python, with NumPy? But we're gonna introduce that in the next lecture on Tuesday. Yeah. So, are there any questions? Is there any material to brush up basic calculus required? Yeah, that's good news. I can try to find some supplementary documents for you. Yeah, that's a good suggestion. Okay. All right, and I think I will stop recording here.